you very much. Questions, please? Yeah.
James, there's obviously a lot of interest by the Miami group and others with use of Schwann's, albeit the attraction, I guess, is the potential for an autologous source, the safety, perhaps they might be myelinated, etc. But how important do you think it will be to modify the environment with hydrogenase or other strategies in order to maximize the efficacy?
Well, I think any cell you migrate, you transplant, Mike, has got this problem of limited integration. Some cells integrate better than others, and one of the reasons we've been thinking of using olfactory glia for spinal cord repair is basically that they seem to integrate better. But olfactory glia are very difficult to get in a quantity that is therapeutically useful, whereas Schwann cells are very easy to get. So I think it's easy to get Schwann cells, and it's easy to get them from individual patients, and therefore from that perspective they're very attractive. The problem at the moment is they don't work. They don't work, I think, primarily because of the lack of integration. So I think this is a promising strategy, but there are issues with the use of chondroitinase. As you know, it's a bacterial enzyme. Transfecting cells with chondroitinase is going to lead to being immunogenic, so you're probably going to have to inject the chondroitinase directly, which is kind of scary, and so on. But nevertheless, I think this is a strategy worth persisting with.
Yes, thanks. My question concerns the inhibition of the integrins. How these chondroitin sulfate proteoglycans doing that? Is there a signaling pathway well known, or how is the integrin being put in the inactive state? Probably through intracellular mechanisms.
Right, you're absolutely right. The mechanism is not known. So the final common pathway for integrin activation is through two signaling molecules, well, not really signaling molecules, tailin and kindlin. And these bind to the beta heterodimer of integrin, beta-1 integrins particularly. So it's through the action of tailin and kindlin on the beta chain that you primarily regulate the activation of the integrins. Now, there are all sorts of signaling pathways that converge, particularly on tailin. So I suspect that that's the convergence point, is that signaling pathways converge to affect phosphorylation and various other properties of tailin. Very difficult to work on tailin because it's absolutely enormous, which is probably why there's not more data. But, you know, so how do you get from, for instance, Fs and ephrins to tailin? Well, we think it's through BAV2, but we don't know where you would go beyond that. But BAV2 again links into many of the standard signaling pathways. How do you do it from chondroitin sulfate proteoglycans? The problem is we don't know what the receptor is. And there are some candidate receptors which are tyrosine phosphatases, but again, they're going to have widespread effects on dephosphorylating things around the membrane and affecting many signaling pathways.
Okay, yes?
I've got two questions actually. Refer to the injured cord, first of all. William Blakemore and others say that when they inject Schwann cells into the intraspinal cord, initially they move very aggressively, and they, as you say, bind elastocytes, and this may not be so beneficial for the cord. The second is that they also have shown that a Schwann cells which spontaneously migrate to demyelinated cords are pushed out later by oligodendrocytes which recover from the injury and depopulate those axons which they myelinate.
Yeah.
What do you think about it?
So there are various issues coming out of Bill Blakemore's work and others. So first of all, there is definitely warfare between Schwann cells and astrocytes. Now, is this dangerous or not, or is it just simply inconvenient? It's certainly inconvenient in that it stops the Schwann cells integrating with host tissue. Is it dangerous? Well, the astrocytes at the interface become definitely hypertrophic. Whether that leads to further damage or not, I don't think we know. As far as the later sort of interactions between myelinated or Schwann cell myelinated fibers and potentially oligodendrocytes, well, first of all, there are Schwann cells that can come from a variety of sources. They can come from your needle, but they can also come migrating in from the entry zones, the dorsal and ventral root entry zones. They can come crawling down blood vessels, but there's also some evidence now that Schwann cells can be stem cell derived, probably from oligodendrocyte precursors. So there are many interactions at that level. Now, whether you eventually see Schwann cell myelination being replaced by oligodendrocyte myelination, I don't think that's clear, but certainly in very long-term damaged cords, you do still see persistent Schwann cell myelination. So it's certainly not all driven away by aggressive oligodendrocytes.
Right, we still have 2 minutes for general discussion. If somebody has some pertinent questions. Yes?
But maybe a pertinent comment, I hope. Right. So you mentioned Bill Blakemore and this issue of Schwann cells not being able to wiggle and migrate, which they don't. You transplant Schwann cells or any number of, let's just take myelinating cells into normal parenchyma, they do nothing. But if you have a defined lesion zone that's relatively acute, they integrate beautifully. And I think you would agree with Bill's work and our work and others that they will move through an environment where you've made an acute chemical demyelination to an EAE lesion, contusive cord spinal injury. They will build a linear array that axons can grow on. So I don't think we should give up on Schwann cells yet. But I think your work is so relevant in that if you have, for example, multiple sites of MS lesion, you transplant in one site, they're not going to jump through the normal white matter and make it to the next lesion zone. But I think it's generally accepted from a large amount of work that pathologic CNS tissue, particularly spinal cord, Schwann cells love to wiggle through that environment, and they're capable of remyelinating and building bridges.
Thank you for the comments, and I don't see any other pertinent questions. Well, one more. Still have 1 minute.
You have a great tool, the chondroitinase and Schwann cells. What do you think? Can you combine these two approaches? For example, infuse chondroitinase in advance and then use Schwann cells?
Well, I think what's going to be most effective in animal models is what I showed you, which is transfecting the Schwann cells to secrete chondroitinase. I think that's dynamite. But I don't think you're going to be able to do that in human patients, simply because there's no switch that will turn off chondroitinase that is clinically applicable at present. So as far as combining the two treatments, yes, you can inject chondroitinase, and I think that there is a preclinical development going on that will make that possible. Yes, you can transplant Schwann cells, but of course doing a clinical trial of both together is going to be kind of complicated because we're going to have to do each individually first. The Schwann cell trial is a Schwann cell trial is ongoing. We'll see where we get to.
What do you think? How long do you need to infuse, for example, chondroitinase? Either to use one injection or use multiple injections or infusion?
Chondroitinase, when you inject it, is quite long-lived. It sticks around for about 2 weeks in the tissue. And so whether that's long enough is something we're going to have to find out. But making multiple injections certainly will be problematic. I think it's going to be feasible to go in and make single injections of chondroitinase. But going back into a damaged spinal cord more than once is going to be a real issue. So I think we're going to have to put in enough that we think it's going to do for 2 or 3 weeks.
Okay, so now it's time to finish. Thank you very much. Thanks to our speakers, and thank you for attending this lecture.